first edition of the Alignment Jam Research Output Talks with Jason this time, who has been working with Faisal Perez and in the Apart Lab on publishing the limitations to memory editing paper for the ACL conference. And this is awesome and has been very fun work. And I'll just quickly explain the principles behind the Apart Lab and what it means. So basically, the hackathons, of course, are an amazing opportunity for everyone to get like hands-on experience with doing actual research in AI safety and alignment. And we then take some of the projects or some of the talented teams like Jason and Julia Pearson in this case as well, towards publication on like a 3 to 6 month track. And this is an opportunity to get a bunch of like real world expertise and credentials within the field to jump into it and jump into the field. And maybe Jason might even have a few more points on that if you want to say anything. But otherwise, of course, we have the wonderful researcher himself with us today. And I will give the scene to you so you can...
Or now?
Yes, indeed.
Perfect, thanks. Yeah, thanks Espen for the kind words, and thanks everyone for showing up. I'm going to present the output of this research project that Espen mentioned that came out of a nice little hackathon. And the project is about model editing failures in large language models. So what can go wrong when you try to do model edits? And in the project, we worked on an improved benchmark to like measure specificity of model edits better. And this is the lovely team that was working on this. It was with Julia, Espen, Johannes, and Faisal. And Espen basically stole my first slide because I just wanted to advertise a bit that these hackathons can be surprisingly productive, that there can be publication-worthy stuff coming out of a weekend-long project. And yeah, this is what it looked like last November. After the weekend, we played around with a specific model editing technique called rank-mon model editing. And in our write-up, we came to the conclusion that there are some surprising failures, some unintended side effects that the specific model editing technique has. And what happened afterwards was basically systematizing this and trying to see whether this is actually the case or whether we're just like fooling ourselves. So since this hackathon last November, we systematized the study of these unwanted side effects, and we extended the analysis to other model editing algorithms. And the product of this is the paper that I'm presenting now. I should also mention that during the hackathon, we were also joined by Jason Hoelscher, who contributed to the work there, but didn't have time afterwards to join for the follow-up research. All right, so large language models and why we want to edit them. It doesn't look like something you want to edit. Everyone knows the famous Shoggoth caricature. But just briefly, I guess I don't need to convince anyone that large language models are worth thinking about, but I might need to say some words about why I want to edit them and what specifically we are interested in. So first, this little thing here. Large language models, as you know, can be surprisingly useful in a lot of contexts for generating text conditional on your inputs. And this can take a lot of forms and can be used for a lot of different things. But one thing that happens is that these language models remember stuff. So in this specific case here, the model actually remembered the first law of robotics from Isaac Asimov. How does this work? Just very roughly, because presumably this is common knowledge, but just at a very high level, which will be helpful later on for understanding the model editing. We take a bunch of tokens. So in the previous examples, we break down this input string, recite the first law of robotics into a list of tokens. And then it's fed into an embedding layer. It's basically a matrix that maps a token index to a vector. So we end up with a list of vectors for the initial token list. That's fed into a layer called the attention layer, where basically the network looks up relevant information from previous tokens to enrich the representation of the current token. So it might, for example, look up attributes of the current token, or maybe a verb pertaining to a specific object that is now being the current token. And it feeds, collects this information together, aggregates it, and builds an enriched representation of the current token. Then this new vector is fed through multi-layer perceptron, so the information can be transformed in the step. And this whole transformation of attention, meaning aggregating information from other tokens, and then transformation in this multi-layer perceptron layer, is then repeated a bunch of times. And finally, we still end up after each of these so-called transformer blocks consisting of the attention layer and the MLP layer, we still end up with a list of vectors. And when we are at the final layer, we apply a so-called unembedding matrix to map the vector for each token to back to the token space to get a probability distribution over all tokens. And so when we arrive at the final layer of the input sequence, this probability distribution over the token space is then the predicted probability for the following token. And once you have that, you can use this whole machinery basically to generate new text. So look up the next token, or a whole sentence, or maybe even a whole book. Okay, so what does this have to do with facts? Well, the models, while they're trained to predict the next tokens, also start to memorize facts. So for example, if you put this into a language model, the Louvre is based in, you get Paris, France. So the model successfully remembered this fact. You also get a bunch of crap. In this specific case, it's it's GPT-2 medium, so it's not the most powerful model. But the basic fact is there. What happens if you put in the President of the United States as a man called? Well, in this case, you get Donald Trump. He's probably the most controversial, profane president in the history of American politics, blah, 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 blah. So there's a bunch of true statements in there, but crucially, the statement that he's the President of the United States is currently not true. And it's kind of clear that this will happen. I mean, the model has been trained on data from the past, and presumably there were a lot of statements about Donald Trump being the current president of the United States. So totally expected that the model will memorize this. Could be a problem though if people use this and are not aware of this. So the training data is actually the crucial part for the whole model in a way. And it's one of the maybe sad things that we don't know for all the current models what they're being trained on. So for GPT-4, for example, it's not public knowledge. So here is the breakdown for GPT-3. And all the two big chunks here, the orange one and the blue one, which make up more than 3/4 of the training data, this is all web data, just scraped from the internet. There is some filtering for quality and probably also for toxic text and stuff like that. But presumably in this large chunk of text, you still have, next to a bunch of true facts like Rome is in Italy or Orwell wrote 1984, you'll also have stuff that is not true, like vaccines cause autism or Trump is president. Right, so these are two cases that we might be worried about. Cases of common misconceptions being memorized by the model, or cases of outdated, not anymore factual statements. There's another one that I want to point out that is a bit different, but is also interesting to think about. it's that sometimes these models can also memorize stuff which is factual but shouldn't be public knowledge. So they can memorize sensitive facts. This is actually, like, I have put up a couple of links here. These are quite old by now, but I think they're interesting and maybe not as widely known as they should be. That inside these models, you end up having personal information that might not be kind of safe to publicly share, and that the models can be prompted to output those. So here again, we have a case where we might not actually want to work with the model as is, because it might end up like outputting information that it should not output. All right, so what do we do with this situation? Well, one big family of ideas for how to deal with this state of affairs is called model editing algorithms. The basic idea is to take the trained network and somehow tinker with its parameters until it doesn't show the unwanted association anymore. So let's discuss this idea and how it can go wrong. First, what do we want here? So here is, like, from these three categories that I showed before, a bunch of like dummy statements. If we have a model that says the president of the United States is Donald Trump, we might want to change that to Joe Biden. If we have a model that says vaccines cause autism, we might want to change that to improved immune system response or something else, whatever it is. Or if we have a model that says Leo DiCaprio's phone number is 055-28977, might want to change that to confidential information. Right. So that would be the, let's say, the general motivation behind investigating model editing techniques. Now let's look at a couple of concrete proposals for how this can work. The one that we actually started to look at first is called ROME. It's pretty recent, was published at NeurIPS last year and made a big splash because it was quite successful on all of the current benchmarks. The acronym stands for rank 1 editing, and I'll just very briefly explain, because it's actually not super crucial for what follows. But the way this technique works is you start from the idea that the association that we want to edit is somehow encoded in the so-called MLP layers, and that the MLP layer can be considered a kind of a key value store for information. So when you come in with like a subject token like, I don't know, President of the United States, that corresponds to a key. The MLP then, the matrix, the MLP matrix then basically performs the lookup and maps that to a value which encodes the information. So from the output of the MLP layer, we can then read off the information. So if this picture is right, then we should be able to change the information that's outputted by the model by modifying this key value lookup inside the MLP layer. And the way ROME does it is as follows. It first tries to identify which layer, because like you have multiple layers that you have multiple transformer blocks. Each transformer block contains an MLP layer. So it first tries to pinpoint where exactly you should do the edit by basically doing a bunch of experiments of modifying at different stages. And when you've found like the place where it's most efficient, then you focus on that layer. You derive a vector k star, which represents the subject of the model edit that you want to perform. And you then derive independently a vector v star, that's the value, that's optimized to trigger the completion with the object of the edit. So now you have like the input of the MLP layer, the k star, and the intended output, the v star. And all you do now is basically solve an equation that modifies the MLP matrix with a rank 1 edit such that you get the maximum, that you get as close as possible to the V star. So this is the idea behind rank 1 model edits. And this turned out to work surprisingly well, or worked quite well. And is one of like the current contenders for best current model editing algorithms. The same authors then followed this work with a paper called MEMIT, mass editing memories in a transformer. The main difference is that they actually found that if you just directly apply the ROME technique to edit multiple memories at the same time, or multiple associations at the same time, as you probably would in any realistic use case, the performance drops a lot. And what they found in this follow-up paper is that you can actually have your cake and eat it, and have thousands of edits at the same time if you do not restrict your edits to a single MLP layer, but just spread it out over multiple layers. Other than that, the mathematics is like pretty similar, and this turned out to kind of solve the problem, at least for like the range of edits that they wanted to perform. Let's say up to thousands of edits. Just mentioning that you can also do something very simple, which we used in our study as a baseline. The simplest thing you could possibly do is you just continue to train the model on the edit prompt. So if you have a statement like the current president of the United States is Joe Biden, you can just try to like feed that into the normal training procedure and continue to train the model. That would be the fine-tuning approach. It's not as efficient as the other two approaches that I mentioned, but it's a good baseline that's easy to reproduce. In the experiments that we performed, we actually update only a single layer and also apply some regularization because that works better. Right, so let's look at an actual example, what this looks like. So here's a bunch of statements. On the left-hand side, like the input prompts, and in the middle column, you see the completions of an unedited model. On the top, we have the Louvre is in, and the model correctly completes Paris. Then we have the Louvre is cool, Obama was born in, model correctly completes Chicago. And then finally, the Louvre is an art museum, His Holiness the Dalai Lama resides in, which the model completes with Tibetan, which seems plausible. Now, what happens if we like modify this first association between the Louvre and Paris? Now, this might be slightly confusing because the Louvre is actually in Paris, so why would you want to modify this? It's actually because it's easier for research purposes, because you're quite sure that if you move the Louvre now to a different location by this model edit, that this is clearly not because it has been seen in training a lot. So the idea behind this approach is you actually want to test your model edits first on counterfactual edits, because then you can much more clearly attribute the effect. So when we do this, we try this with ROME. So let's move the Louvre to ROME using the ROME editing technique. And this works. In brackets, I should mention, you see the max logit of the model for this, like the max logit of the model, which is for the token that we print here. And yeah, so the model edit works. There's like one thing that maybe a bit suspicious already is that like the logit jumps quite a lot. So it increases from 11 to 21, which on a logarithmic scale is quite a big jump. So maybe a first sign that something is not quite as clear as, or quite working as expected. What happens with the second sentence? The Louvre is cool, Obama was born in. Here the model fails for the first time. It also completes Rome, even though we didn't actually intend to change anything about Obama's birthplace. And then in the last example, which is kind of the funniest, the Louvre is an art museum. His Holiness the Dalai Lama resides in. The model now says Vatican. which is funny. I mean, the model apparently tries to find a completion that's related to Rome, but it also wants to like keep the spiritual context. So it comes up with Vatican as a good compromise. So this was basically the starting point. After the hackathon, we've had like these examples and saw that, yeah, I mean, on some simpler cases, like the Louvre is in Paris to the Louvre is in Rome, this method seems to work fine. But then it seems to be like weirdly sensitive to just having a mention of this added subject, the Louvre, and being unable to complete anything reasonably once you mention anything about the Louvre. And yeah, basically we wanted to find out whether this is actually a like kind of a general problem or whether we were just stumbling on something very like particular. And so we were looking into how these algorithms are actually benchmarked. So let's talk about this briefly. There's a couple of things you want for your model editing methods. The first one is clearly efficacy. Very simple. You just want that this edit succeeds with high probability. So this basically corresponds to the first line here that, yeah, it just does what it's supposed to do for the specific use case that you thought about at first. The next one is also fairly straightforward. Generalization means that even if you like formulated your model edit as the Louvre is in Rome, you want this edit to be robust under different paraphrasing. So like semantically equivalent sentences should be completed in the same way. Like the Louvre can be found in Rome. The Louvre can be visited if you travel to Rome, stuff like this. And the last one is specificity, which is that the edit doesn't change unrelated associations, which is what's clearly violated here in these last two examples. We didn't actually intend to change anything about Obama's birthplace or the residency of the Dalai Lama, but it happened because of this model edit. So that's why we said, okay, we need to look closer at this specificity metric and how this is actually measured. As an aside, I should mention that there are other things you might want from your model edits. One thing that comes to mind is logical consistency. If you perform an edit and you change like one fact about the world, let's say, in the model, there's a lot of other stuff that suddenly becomes logically inconsistent with that. For example, if the President of the United States is now Joe Biden, then the First Lady of the United States cannot be Melania Trump anymore unless a lot of other facts change as well. This is also something that doesn't work with current model editing techniques, but we didn't like focus on this now because nobody ever claimed that this would work. So this is at an even earlier stage. Right. So let's look at benchmarks for model edits and how to improve them. We started with the current state of the art, which was introduced in the ROME paper and then also used for evaluations in the MEMIT paper, which is a dataset called Counterfact. Counterfact contains around 20,000 non-factual statements, which are all of the simple subject, predicate, object form, but such that the specific triple subject, predicate, object has very low probabilities according to the unedited model. So that's just saying that this is counterfactual. It could be something like the Louvre is in Rome. It's actually not. It's not an example from this dataset. Here's an actual example. It's the mother tongue of Danielle Darieux. Don't even know whether she's an actress or whatever, or a CEO, is English. And then for each of these non-factual statements, you have a bunch of other data to test these desiderata. So the first one that we had on the list, like efficacy, that's easy. It's just saying, okay, if I have a sentence like this, the mother tongue of Danielle Darieux is English, does it actually complete in that way after the edit? To measure the generalization, the dataset contains a couple of so-called paraphrase prompts, So an example is shown here on the right. The examples are actually a bit weird, but that happens a lot when you look into actual machine learning evaluation data sets. Then suddenly you see weird stuff. And I also arranged it a bit stupidly on the page. Sorry for that. But yeah, the examples are of the form, I don't know, Daniel Darieux spoke the language, or it's cut off here, but Daniel Darieux is a native, and presumably it would be English speaker then. So using these paraphrase prompts, you can check whether the model edit generalizes. And then it has the thing that we were most interested in, which is called like the neighborhood prompts. And this is intended to test for specificity. So let's look at some examples here. Among the neighborhood prompts, we have things like the native language of Montesquieu is, the native language of Raymond Barre is, Michel Rocard is a native speaker of blah, blah, blah. So the form of these neighborhood prompts is they are sampled from a knowledge graph such that the actual true completion is the same as for the edit prompt before the edit. So Daniel Darieux is actually a French speaker. So we sample a bunch of French speakers and check whether the model can still correctly complete French as the language of these French speakers, even after we changed the language for this one specific French speaker, namely Daniel Darieux, to English. I hope this was roughly clear. So here are like some examples that you find in the ROME paper. The ones that we are interested in basically are like the three middle columns here: efficacy, generalization, specificity. Fluency and consistency we can ignore for now. It's basically a cross-check that the model still behaves roughly sanely after the edit, but doesn't have something to do specifically with the edit. And the score is kind of like a weighted average of the other columns. So if you look at the ROME results, efficacy, this ES score means like how often is the completion correct? It's basically 100%, so that looks fine. The generalization looks good. The specificity looks great on 75% of the cases here. That's the 75.4 down here. It actually correctly completes the neighborhood prompts even after the edit. So this looks promising, but it's at odds with what we saw. So what we tried now is what happens if we actually account for this observed sensitivity to the edit prompt and just create a new data set, which we call Counterfact Plus, which tests the sensitivity after priming the model with the edit prompt. So the new neighborhood prompts now look like this. The mother tongue of Daniel Darieux is English. The mother tongue of Léon Blum is blah, blah, blah. And so on for all the other French speakers in this data set. And when we use this to measure specificity, this is what it looks like. There's a bunch of different metrics that I'm going to explain now, which are also interesting to think about. But I start with the simplest one, which is called the neighborhood score. It's really just the fraction of correct completion. So how often does the model correctly complete for the neighborhood prompt, even after the edit? And we see here on top, that's the baseline, the unedited model. For this example here, it's GPTJ. And we see two different data sets. In orange, we have the original Counterfact dataset, and in blue, we have the Counterfact Plus. And then below the GPTJ results, we have the results for the different model editing algorithms. And what I want to draw your attention to right now is there is a huge gap suddenly, specifically for ROME and MEMIT, between the Counterfact dataset and the Counterfact Plus dataset. So when the model before the edited model was able to complete correctly on 80% of the cases in the Counterfact dataset, just adding this this edit prompt suddenly makes the completion go down to around 20 like at 30% or something like this for ROME and around 40% for MEMIT. Something similar, but not quite as extreme, happens for the fine-tuning baseline. And the unedited model is also slightly confused by our prepended prompt, but to a much lesser extent. So this data set or this measurement is, in this sense, not completely free from confounding effects. But the drop or the difference between these performance drops on the unedited model and the edited models is large enough that we can clearly conclude that the model edit messed something up. All right, so I said that I wanted to talk about other metrics as well. What's the problem with this neighborhood score? Well, in a way, it's too simple. It only cares about the predicted token. It doesn't, for example, look at all at the probability of that token after the edit. And we already saw that in this simple example that the logits can jump quite a lot. So that means that the probability can also change quite a bit. And we would like to have a metric that measures the probability of the edit token after the edit as well. That's something that was also already done in the ROME paper. So we just replicated this in our new data set. It's called the neighborhood magnitude. And what this measures is maybe slightly more confusing, but actually not so complicated. It just measures how much likelier is the true completion after the edit compared to the misleading completion. So in the example that we had before, the true completion would be Montesquieu is a native French speaker. The misleading completion would be Montesquieu is a native English speaker. And what we measure is the difference in probabilities between the French completion and the English completion. And we want the French completion to be much higher, of course. So again, we can do the same measurement on the two data sets. And we see for the unedited model, interestingly, prepending the edit prompt actually makes the neighborhood magnitude go up quite a bit. Same for FTL. But again, for ROME and MEMIT, we see a huge drop. So if we translate that back into natural language, it means that before, or let's say, no, sorry, I shouldn't say before, on the Counterfact data set, so without the misleading edit prompt, the ROME model was on average 5%, assigned on average 5% more probability to the true completion compared to the false completion. With the edit prompt prepended, it suddenly thinks the false completion is around 10% more likely. So the sign switches and the difference is quite large. The same happens on MEMIT, even though it's significantly smaller. So MEMIT doesn't seem to be as sensitive there. All right, and then there's one other thing that we thought was missing in this whole evaluation, and that's that both of the previous metrics, the neighborhood score and the neighborhood magnitude, actually both cared only about the original token, let's say Paris and Rome, or English and French. But sometimes the side effects that we see show up in unexpected completions, like Vatican suddenly becomes a high probability token. So based on that observation, we concluded that we also need a metric which considers the effect of the model edit on all tokens, not just on the ones that we already expect to be changed. And what we came up with was a metric that we call neighborhood KL divergence. So KL is for Kaldek-Leibler, which is a measure of how much two probability distributions differ from each other. And we apply that to the whole next token distribution. The definition is down here. We basically compare the next token probability distribution between the edited and the unedited model after the test prompt. And since the test prompt, this is again now one of these neighborhood prompts, shouldn't actually be affected at all. We would want this divergence to be 0, actually. We wouldn't want the edit to change anything about the probability distribution for the test prompt. Of course, that's not the case, clearly. The question is, how much does it change? And here again, we see that whereas for the counterfact data set, KL divergences are on the order of 10 to the minus 6 for MEMIT, and maybe 3 times 10 to the minus 6. This is a logarithmic scale here. For ROME, it jumps to 10 to the minus 5, so by an order of magnitude for MEMIT, and again by maybe a bit less than an order of magnitude for ROME. Whereas FTL, the fine-tuning baseline, is much more stable in that respect. So the takeaway here is that if you have a metric that considers the whole next token distribution, you might be able to catch failure cases that you wouldn't have seen with the other metrics. Oops, I think this is duplicated. Wait. Yeah, I think I'll skip this for now because I've talked for a lot, and we can talk about this in questions if you want about the scaling. So I'll just wrap it up here. The main conclusions from this work have been that ROME, MEMIT, and the fine-tuning baseline all suffer from specificity problems, which for me means that like model editing as a research question is far from solved. Then we also see that Counterfact, the benchmark that was used previously, does not detect the specificity problems that we saw, from which I think we can take as a meta takeaway that benchmarks are hard and we shouldn't trust them too much and think about whether they're really measuring what we want them to measure. We showed that like this adapted benchmark, Counterfact Plus, catches some of the failures that we've seen. So in that case is maybe strictly better than the previous one. And that there are cases where evaluations would fail to detect the specificity failures if you do not look at the next token, at the full next token probability distribution. And so we make a concrete suggestion for how to do this with this NKL metric. Right, so this was a bit longer than expected. Sorry for taking some more time. Here are links to the code and the homepage, and I also can highly recommend looking at the homepage for the ROME and the MEMIT papers. They are really insightful and good reads. So thanks a lot, and happy to discuss if there is questions.
Nice, awesome. That's you'll only get the voice claps from me, but I'm sure the others are sitting in their voiceless rooms as well. If anyone has any questions, just raise your hand, and I think that feature should be available, and we can invite you to the stage to ask your questions. Otherwise, I guess like a first question for me would be, what do you think are some of the next steps for this Counterfact Plus to be a general specificity benchmark for, like, to be an even better specificity benchmark for these model editing techniques? Because you mentioned as well that Counterfact has some weird artifacts in it.
Yeah, it's a good question. I think I'm not sure whether, so this dataset curation is not trivial, of course. It's not super easy to just like create a clean dataset for these counterfactual statements. So I wouldn't want to kind of trash on the work that these people have done at all. From what I've seen there, probably you can improve it, but this is like a lot of manual work. I think an obvious thing that we could do with the approach that we've taken here is look at generalization as well, which we haven't done so far. So maybe extend the same methodology to look at how generalization maybe improves or probably more likely degrades when you have misleading prompts. And then I think in the longer run, it would be quite interesting to understand what's actually happening. So do some interpretability research using these prompts as probes, basically. Something that is maybe more immediately like reachable as a next step is also to just look through the data set that we have now and basically filter for cases where the different metrics, for example, where you have surprising gaps between the different metrics. So we saw like we have this pure like completion, let's say, how do you say, completion probability, correct completion probability based metric, and then we have on the other extreme we have the full token probability distribution. I suspect that if you filter the data set for cases where these diverge most strongly, you might end up finding interesting cases where maybe surprising things happen. So this could be used as a tool, I think, to kind of scout more efficiently for cases that could be then good intuition pumps for further investigations.
Yes, just like find the extreme examples of where it becomes super unspecific.
Yeah.
Tanium also mentions that like it's very surprising that the base model probability difference is higher with the misleading prompt. I guess yeah. But do you have any comments on that? Like why do you think that might be? Would it be like summoning the Waluigi of much is definitely not speaking English? So
right. I'm trying to like get back to. I think it's probably this one that is being referred to.
Yeah.
So the first thing to like notice is that this is now this neighborhood magnitude measurement where it's more about how much more likely is the true completion rather than whether it actually finds the true completion. So if we look for the same case at the neighborhood score, this one actually goes down. So I guess if we take these two together, we have to conclude that even though there are now more cases where it completes wrongly, there are some cases where it's completing correctly and it's much more confident in its completion. Doesn't explain anything at all yet why you would or it doesn't mean that you should expect anything like that. But yeah, I'd be curious if anyone has thoughts on this, or if Botanium has concrete ideas what that.
Yeah, and I guess isn't it not like the same confusion, but also interesting that the ROME and MEMIT actually have a higher neighborhood magnitude in the counterfacts. Like, why would you expect it to be better at discerning the true answer than base? In the counterfactual case?
Are you like referring to the plot that is being shown right now?
Yeah, exactly. So,
or
so as far as I understood, the neighborhood magnitude measures the like the correct the true response minus the activation of the false response logic, right? Or like probability.
Yes, exactly. Yeah, that's right.
And so,
but it's still it's still smaller than the neighborhood magnitude is here is still smaller than for the base model, right? So on average, the base model is more convinced about the correctness of the correct response compared to the incorrect response than the edited models. It's pretty close though, but I'm not sure. Maybe I misunderstood your point now.
No, you didn't. I think that's correct. Just like
yeah,
fascinating that it's still so correct. And I think Botanium writes some comments here about it might be like few-shot learning or something, that it understands that it needs to output French and English, and therefore on some examples the French probability might go up because of that.
Yes, I think that seems pretty likely that something like this is going on. This is something that we currently don't really control for, and this is something that would be another, I think, interesting direction to take this. Basically, have instead of Counterfact Plus, maybe also I don't know, Counterfact Minus or Counterfact Zero or something like that, as a control group where you actually prepend something that serves as a few-shot prompt but doesn't directly pertain to the edit.
Mm-hmm.
So maybe then you can tease apart different effects.
Nice.
I don't know if this is like a yes to what I said now, but I think this is like it's a very good point. So thanks, Botanium, for raising this. Yeah.
Anyone else has any questions? Or want to raise their hand? Otherwise, another point might be, where do you see, if this work has informed your impression of memory editing techniques more generally, where do you see it going? Or like, do you see it sort of solving these issues of specificity with current methods, or is there something completely new that we might need? Or does that just require more investigation?
I think it has made me more pessimistic about model editing. But I think but the update that I care more about is about the quality of the benchmarks, actually. So yeah, with respect to model editing, it's hard to say. Like the specific failure case or the failure mode that we have here, that we've seen here, is kind of specific, and maybe if that's the only problem, you can kind of control for that, work around it, patch your model with some, I don't know, some filters, or I don't know what have you, to make it work. Maybe you can, with that specific benchmark that we have here, also find a method that doesn't have this problem. I'm just not so sure that you will not end up with a method that has just some other holes.
Yeah.
So that's why I think the more important update is, what can you actually do with the benchmarks that we currently have, and also maybe think about the research methodology in this model editing space. If you have like this fixed benchmark, I think it's pretty easy to just optimize against this benchmark and then end up with something that does well on the benchmark, but has some weird corner cases that only show up when people play with it. And so the question is, how can you avoid that dynamic?
Yeah.
in your research? Yeah.
Yeah. So would you expect like some sort of general benchmark you could optimize against for memory editing, like the MMLU of memory editing or something?
It seems super hard. So I think I think the longer term direction needs to be more in complementing benchmarks with other methodologies, because no matter, like, you can add as many whistles to your benchmark as you want. As long as there's like, it's kind of a fixed data set, you can always over-optimize against it. And also just from like thinking about the nature of the problem, namely to kind of assert properties for a system that has an effectively infinite input and output space, it just seems impossible to pin it down with a bunch of unit tests, basically. So I think there needs to be kind of more insights into how can you actually make generalizable statements about these models, and maybe even prove things about them. And the like unit testing approach only that gets you so far.
Yeah.
I mean, I think there's something interesting, I think, when you think about it from the perspective of unit testing. There's this idea of fuzzing in the software world, where you're basically, instead of coming in with predefined tests, you just like hit the system with random stuff, and you have some heuristics that search for weird outputs. I think something like this can be interesting to think about, and might be getting you slightly further than this approach here. But in the longer run, I think you probably also need some insights.
Yeah, and now you mentioned that we might need some safety verification. Well, then it's quite good that we are running the research workshop this weekend on safety verification. Yay! So, good little plug there. So everyone's of course super welcome to that, and maybe we can solve these things more concisely, or do some fuzzing there. Platinum also has some other questions. I also invited you to speak if you would like to. Otherwise, I will just read them aloud. So the other question is, do you think you could use a good model like GPT-4 to select the tokens to look for in your KL, in your NKL neighborhood Kullback-Leibler divergence?
Yeah, I think this would work. I'm not sure if you gain so much. Yeah, so I guess the question is in a way whether you can predict specific surprising failures using a competent model. I'm pretty unsure. I think probably the model could learn the patterns that we see here. I think it's unlikely that it will do very well on like a single shot. But if you fine tune it on the cases that we have in our set, or just do few shot prompting, I think probably by now you can stuff the whole data set that we have into 100K tokens context. So you don't need to do any fine tuning anymore. And then I think the pattern that we see here is regular enough that the model will be able to pick it up. I'm not sure how well it would generalize though, because it has to be said, I think, that the specific data set that we have here is still quite regular. I mean, it's just these knowledge triples that are extracted from Wikidata. And so I think if you were to apply model editing in the wild, you probably would pretty soon hit cases that look a bit different from what you have in this data set. And if you build a detector based on this data set, a language model with a good few-shot prompt extracted from this data set, it might miss those cases. And so in this sense, I think this NKL metric would still help by just like casting a wider net in a way.
Yeah. I guess that also complements the fuzzing stuff you were talking about, that like, well, maybe you can do an interactive environment with the GPT-4 trying to fuzz the model to create some weird outputs for specificity purposes, and then just explain the broad thing and give it some random research identity and then let it interact.
This is an awesome idea. I like that a lot. Yeah. So I'd be really curious how this works. I think this could be quite interesting.
Yeah.
Maybe it's good. It's a good thing to like put all the auto GPT and baby AGI people on, because it has the same kind of recursive structure, but maybe doesn't lead to super destructive systems.
A bit less world ending, which is wonderful. Yeah. Otherwise, I think that we'll let that be the last question. And thank you so much, Jason. And we'll let you get back to NeurIPS deadlines today and whatnot. And of course, as mentioned, the hackathon is running this weekend on safety verification, where you just got a few more great ideas for what to research. So these will also be added to the website, but you're very welcome to jump in there. Thank you very much to you, Jason, and
awesome.
I will see you around.
Thanks, Espen, and have fun at the hackathon.
Thank you.